Welcome to a virtual GED class. So we are getting into kind of our last area of data analysis that we're going to be looking at. So one of the areas of data analysis that we see on the GED, so could happen on your math or your science tests, is the idea of counting and probability. And I know some of you guys are thinking, Kate, I don't need counting. I've been counting since I was like 3 years old. 1, 2, 3. How hard is it to count? Not quite what I'm talking about. I'm talking about counting up certain scenarios, how many different combinations of things that could happen. Now, counting is actually a really complex subject. I took a whole class on counting and probability when I was in college, and it was really challenging, even as a math major. The good news is that that's not the kind on the GED. There's only really simple counting problems and really simple probability problems on the GED, so they're not too complex. So we ought to be able to solve them with some pretty simple problem-solving methods. I've seen a lot of teachers teach the standard method here, which is to give you guys some pretty complex-looking formulas that scare students and are not on the GED formula sheet. I'm not going to use that method. We're just going to use problem-solving techniques today, since, like I said, the examples that appear on the GED are usually relatively simple. Here we go. Let's talk about counting. First of all, what kind of problems are we talking about? We're talking about if you say something like, oh, I don't know, if a hamburger bar features 2 bun options, 4 cheese options, and I don't know, 5 topping options, how many different possible burger combinations are there of, 1 bun, 1 cheese, and 1 topping? So you can see why I say this is not just simple as counting 1, 2, 3, because we're looking at combining things and mixing things up, and we've got different numbers of certain things, and how are we going to choose them? And so, there's a little bit of complexity here. So these are the kind of problems we're going to be looking at. Now, for those of you who you know the mathematical terms combinations and permutations, we'll be looking at both of those today, but I'm not going to use the technical math term because it's not necessary for the GED. And like I said, I'm just going to use some pretty standard problem-solving methods for this today. So, but I will say that sometimes with counting, order matters, and sometimes it doesn't. That's going to be the big thing that we have to think about as we do each problem. Will the order matter? Okay, so we're just going to dive right into it. Woo! You could saved a long lecture today. Let's go look at the example problems. And you may have noticed that I titled this Simple Counting Problems, and hallelujah, we needed a problem like this on the GED. We needed an area that they didn't get too complex in. Counting and probability are that area. They really do simpler style of problems on these. So yeah. Let's take a look here at example 1. Example 1 says a florist sells a mixed bouquet option where you can pick any 2 flower types from a list of 5 common flowers. How many different 2 flower combinations are possible? So this happens a lot in life. We can go in, and we're allowed to choose things. And so the question here is, how many different possible bouquet options could I end up making here? In order to do this, like I said, I'm not going to use a formula. I'm just going to use some problem-solving techniques. This is what I'm going to do. I'll give a name to some of the flowers. So let's say, I don't know, we've got a rose, a tulip, daisy, baby's breath, and I don't know, a lily. So here we have these list of 5 common flowers, and in our mixed bouquet we're allowed to pick 2. So let's start with if rose was one of our options. And what I'm going to do here is I'm just going to really logically look at what I could pair rose with. So I could do rose and tulip, couldn't I? Or I could have chosen rose with daisy. I could have just as easily done rose with baby's breath, or I could have done rose with lily. Now, as I go to do the next line, I need to think about this, okay? Is having rose paired with tulip any different than having tulip paired with rose? Does order matter, or will I end up with the same bouquet? So is it the same bouquet if I do rose tulip and tulip rose, or is it a different bouquet?
It's the same.
It's the same bouquet. Rose and tulip is the same as tulip and rose. And so on the next row, when I start with tulips, I'm going to skip tulip with rose because I already accounted for it right there. But I'll pair tulip with daisy, and I'll pair tulip with baby's breath, and I'll pair tulip with lily. And now I've done all the rose possibilities and all the tulip possibilities, and I'm being very logical about this to make sure I don't miss any. Now it's time to start with the daisies. Well, as you can already see, I already have the case where I paired daisy with rose and where I paired daisy with tulips. So obviously I don't have to go back to the ones above it. I'll just pair daisy now with baby's breath and daisy with lily. Does that make sense?
Yeah, so we're going like loosen and loosen.
Yes, exactly. So then the only thing I'm going to end up with in the baby's breath row is baby breath paired with what?
With lily.
With lily, exactly right. And there's not even going to be a row for lilies because, hello, I already paired lily with rose, lily with tulip, lily with daisy, and lily with baby's breath. And because I was really logical and orderly about this, I'm sure that I have every possible combination. And I can just count them up. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible 2 flower combinations. Easy problem. So now, could a combination problem get a lot more complex than this? Yes, they could say that you could pick 3 flowers or 4 flowers. There could be 10 options and you're choosing 4 flowers. It would take a really, really long time to do that. If that was the kind of problem you were doing, like you were in a college class doing that, you would want a formula to do your math. But in a simple case like this, it was easy enough to list all the possible combinations. So let's look at number 2, which is similar. A pizza restaurant is offering a special on 2-topping pizzas. If the restaurant features 8 different pizza toppings, how many different 2-topping pizza combinations are possible? So once again, you know, I have these different combinations. And once again, I have to think about this idea of if it matters, if I repeat, will it make a different pizza or will it make the same pizza? Like, is a pepperoni mushroom pizza the same as a mushroom pepperoni pizza?
It's the same.
It's the same. So I can do it this exact same method. Okay, so I'm too lazy to spell pepperoni and write it a dozen times, okay? Y'all know how lazy I am. So I'm just gonna label the toppings from, if we have 8 toppings, can I just call them topping 1 through topping 8? So I could combine topping 1 with topping 2, 3, 4, 5, 6, 7, or 8. Cool. Now I've already accounted for all my possible topping 1 things. So as I start this row for topping 2, I won't have topping 2 combined with topping 1 because like Maricela told me, a pepperoni mushroom pizza is the same as a mushroom pepperoni pizza. So I'll just start with 2, 3, 2, 4, and so on. Anybody want to speak to why I don't have a 2, 2? Why didn't I write 2, 2? It has to do with the wording of my question.
Because they're asking for 2 different toppings.
Exactly. It's looking for a 2-topping pizza. So a pepperoni is not a 2-topping pizza. It's just a pepperoni pizza. That's 1 topping. Okay. So now I'll start my 3 rows. So the first one I'll list here. Well, I already have 3 paired with 2 and 3 paired with 1. So I'll just start with 3 pairing with 4 and so on. Okay, help me out for the next one. I'll pair topping 4 with what?
5.
Yeah. 6, 7, and 8. Now I'll pair topping 5. What's the first one I should write here?
6.
Exactly.
It's so easy when we organize the numbers.
Exactly. If you weren't organized, you would really struggle with this. But if you can go in a logical order, you'll be fine. So what's I ran out of room. I'm going to come over here and write on the right and write it. But what's the next one you should see?
6, 7.
Exactly. I'll pair topping 6 with topping 7, topping 6 with topping 8, and then finally topping 7 with topping 8, and I'm done. Is everybody cool with that?
Yes.
Mm-hmm.
Great, let's add them up. So 1, 2, 3, 4, 5, 6, 7, plus 6 more is 13, plus 5 more is 18, plus 4 more is 22, plus 3 more, 24, 25, 26, 27. I think I miscounted because I got 28 the first time I did it. Whoops, let's do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Okay, even the math teacher can screw crap up. So 28. Is that pretty simple, David? I'm going to assume that David says, yes, Kate, you're a fabulous teacher. You're my favorite in the whole world. And I think it's amazing the way you teach everything. Just put that out there.
I love that. I'm going to do that with my husband too.
This is what I do to my husband too. If he doesn't answer me, then I just can make up my own answer. It's perfect.
Yep.
Okay. So I'm going to clear this screen and I'm going to move up number 3 so I have lots of room because number 3 is going to get a little more complex, okay? You guys ready?
Yes.
Number 3, a certain restaurant sells 1 scoop ice cream sundaes. You have the choice of an ice cream flavor. You get to pick your ice cream. You get the choice of a sauce, hot fudge or caramel, and you get to choose your topping, nuts, sprinkles, cookie crumbles, or strawberries. Given the choices, how many different 1 scoop ice cream sundaes are possible? So you can see we have this same kind of similar idea. We have some choices going on and we're looking for the number of possibilities. But this time my choices are a little different. It's not like just choose any 2 of the flowers or choose any 2 of the toppings. This time I have distinct categories. I choose 1 ice cream and I choose 1 sauce and I choose 1 topping. I'm going to plan my work a little differently, okay? Let me start with, if I have a vanilla ice cream as my ice cream choice. Okay, now I know this isn't the only choice, but I want to just start with this. So the first thing I do is choose vanilla ice cream. Now, how many choices do I have next? Well, now this vanilla ice cream, or whether it's vanilla, chocolate, or strawberry, you know, this was 3 choices, but all of a sudden my number of choices are going to multiply because now I get to decide my topping. If I had vanilla, I could get hot fudge or I could get caramel. But guess what? If I chose strawberry, I could still choose hot fudge or caramel. Even if I chose strawberry, I could still choose hot fudge or caramel. Now, I haven't finished this problem yet because I still have to deal with the toppings, but I want you to look at what's happened. What originally started as 3 choices of sundaes is now up to how many choices?
6.
6.
Exactly. When I took that 3 and now I ended up with 6 when I considered the 2 topping choices. And now let's look from there. With the hot fudge, with the vanilla hot fudge sundae, I have 4 choices of toppings. I could top it with nuts, with sprinkles, with cookie crumbles, or with strawberries. And then if I have a vanilla caramel sundae, I could still top it with nuts, sprinkles, cookie crumbles, or strawberries. And if I have a chocolate hot fudge sundae, same thing. I have 4 options. And if I have a chocolate caramel sundae, same thing. I get those 4 options. And if I have a strawberry hot fudge sundae, guess what? I get 4 options. Or if I was down here, I'd get the same 4 options. And now how many possibilities would I end up with?
24.
24. So I want, you guys know how stinking lazy I am. I want a mathematical relationship. What was happening with those numbers as I went from here? Well, first I had the 3 choices for my ice cream, but then I factored in the 2 choices for my toppings, and I got 6. Well, mathematically, how would I combine 3 and 2 to get to 6?
Multiply.
Multiply. And then I had the 6, ice cream sauce options, and then when I brought that in together with the 4 toppings, that again multiplied it. So each time you make a distinct choice, you could just multiply. Okay, now this is only going to work if it's a distinct choice. Our last problem was not a distinct choice. We were just choosing any 2 toppings. So it was a different method. Does that make sense? But this will work when you have a distinct choice. So each time you make a distinct choice, multiply by the number of options you have. So I will show you this problem solving method that I have over here is a legit one where you make this like kind of map. They use them a lot in the area of probability and counting, but it takes a long time. And you can see I didn't even have that much options. Imagine a restaurant where you had 31 ice cream flavors or 6 sauces and 84 toppings. I mean, good luck with your diagram. You need one the size of my classroom or bigger. Okay, so we need that shortcut method. So we're making 3 choices here. We're choosing our ice cream, we're choosing our sauce, and we're choosing our topping. And so the quick way to do this is just to say, well, there's 3 ice cream choices times the 2 sauce choices times the 4 topping choices. And there you go. 3 times 2 is 6. Times 4 is 24. This is the shortcut method to deal with this. So these are the only 2 real methods we're going to use today. Either listing it all out, if the order it doesn't really matter, Or if we have these distinct things like this, where it does matter, then we can just multiply option by option by option each time we make a choice. Okay, so all we'll have to do is pick out which scenario it is. So this is really real in my life because my husband has this thing for Red Robin, right? So we end up getting burgers a lot. So let's take a look. A certain burger joint lists the following options on their Build a Better Burger menu. According to the menu, you may build the burger of your choice for only $7.95 by choosing any one item from each category. There's a category for buns, you're going to choose a bun. There's a category for burgers, you're going to choose a burger. There's a category for cheese, and there's a category for toppings. In this case, they're distinct categories. Do you see that? I'm not choosing two things from the same arena. They're distinct categories here. And so I could just go ahead and use that lovely technique where I just say how many choices I have. And each one of the choices, like I'm going to choose my bun, and I'll times that by the number of options I have for my burger when I choose my burger, and my cheese, and so on. So you guys tell me, how many options do I have of a bun?
4.
4. I have the soft white, the whole wheat, the lettuce wrapper, the pretzel roll. 4 bun options. And how many burger options do I have?
3.
3, the beef burger, the turkey burger, or the veggie patty. How many cheese options are they giving me?
3.
3.
3. And how many topping options are they giving me?
3.
3. And you can literally just use your calculator to do the multiplying. You would always have a calculator on this kind of a problem, even if it was on the science. It wouldn't be about burgers on the science, though, you know. But you would see the choices. And so that's 108 possible Build a Better Burger if I don't negotiate with my server to make any other changes to the can I get two cheeses and no toppings? Okay, we're not talking about that. We're just talking about the choosing one item from each category. Let's look at the next one. In the student council elections, 3 students are running for president, 4 are running for vice president, 2 are running for treasurer, and 1 is running uncontested for secretary. How many different possible student council teams could be elected from these students?
3 times 4 times 2 and times 1.
Yeah, and I like how you hesitated at the times 1, like, should I say it?
Yeah.
Yeah, it doesn't really matter if we times by 1 or not. So include it or don't include it, you'll get the same answer. Okay, but yeah, exactly. I have 3 choices for president. I have 4 choices for vice president. I have 2 choices for treasurer. And in this case, it's, you know, even if it was the same pool of students, having Jack as treasurer and Jill as vice president is not the same as having Jack as vice president and Jill as treasurer. So order really does matter. So I would use this method. Is anybody mad at me?
Nope.
No.
So 3 times 4 times 2 gives me 24 possible student council teams. It's going to be the fastest class ever, huh? Yeah, I love it. I love it. I love it. I love it when the GED only hits a simple level of a problem. So number 6, 2 identical 6-sided dice are rolled. How many distinct rolls are possible?
6 times 6.
Good question. So it's 6 times 6 if order matters. And it is the other way around, the way we were counting before, if order doesn't matter. So let's think about it right now. Is rolling a 1-6 the same as rolling a 6-1? Look at the phrasing of my question. Do you see how it says how many distinct rolls are possible?
Oh, yeah. Okay.
And that's the hard thing. A lot of times, and that's actually the hardest part of counting, David. Sometimes you and I don't agree on if order matters. So it would be really important that who's ever writing the question uses some really clarifying language that would tell you whether or not order mattered. And I was very careful to choose my wording here so it could be definitively agreed upon. Does that make sense? So it says how many distinct rolls are possible. So we're going to say 1-6 and 6-1 are the same roll. Does that make sense?
Mm-hmm.
So if I did 6 times 6, it would count 1-6 and 6-1 as 2 separate rolls. So I'm going to do it the other way we did it, where I just listed them out. Are you cool with that?
Yep.
So, but this time it is possible to roll a 1-1, isn't it?
Yeah.
Yes. So I'll start with 1-1, 1-2, 1-3, 1-4, 1-5, and 1-6. It is totally possible to have both die have the same number on them. Okay. And so this row will start with 2-2, 2, 3, 2, 4, but notice how there's no 2, 1. Why? Because they said distinct roles. So as far as I'm concerned, 1, 2, and 2, 1 are not distinct roles. They are the same basic role. Okay, and now 3, 3, 3, 4, 3, 5, 3, 6. What's the next row going to say, guys?
4, 4, 5.
You skipped one. Is it possible to roll a 4, 4?
4, 4, yes.
Then 4, 5.
4, 5, 4, 6.
How about the next row?
5, 5. Sorry.
There we go. Isn't it funny how being in math class can make your brain have the weirdest blips ever? You were like, I knew what 1 + 1 was until the math teacher asked me.
Yeah.
Okay, so 5, 5, 5, 6. How about the last row? What are you going to see in there?
It'll just be 6, 6.
Exactly, just 6, 6. I'm not going to go back and look at 6, 5, 6, 4, 6 because those were all accounted for in the other roles. I'm looking for distinct roles. Okay, great. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 distinct roles. Great. Now, David, if one was a red die and one was a blue die,
It'd be different.
it'd be 6 times 6 because a red 5 is not the same as a blue 5. And now
Yeah.
I have a red 5 and a blue 5 versus, or, a red 4 and a blue 3 versus a red 3 and a blue 4. Does that make sense?
Mm-hmm.
Sweet. Okay. So let's look then at number 7. A scientist is performing an experiment in which one of 5 metals is exposed to one of 4 different corrosive substances for 24 hours to determine their relative reactivity. Obviously, here's how it could come up on the science. How many different samples of one metal and one corrosive substance will the scientist end up testing?
So 5 times 4 different substances.
I absolutely agree. I can just use the shortcut 5 times 4 method this time. Would you care to explain to me why that'll work?
Because there's 5 metals and only 4 different corrosive substances that you can use. So.
Exactly. Those are totally different categories of things. And so, this little shortcut will work. Okay, so 5 times 4 gives me 20 different possible samples that he's going to be testing and probably measuring some things about. Cool, then let's look at our hardest problems. The only way that this will really get harder on the GED is for me to surround it by confusing language. And I did my best to try to throw some loops your way, so let's take a look. 8 is not hard, but 8 has a lot of scientific language around it.
Yeah.
Okay. Throw you?
Yeah.
Well, here's the good news, Maricela. I'm prepping you for two tests at once while we do this. This is commonly how counting and probability come up on the GED. They come up in the subject of heredity. Do you know what heredity is?
No.
Heredity is passing on traits from parents to children. Maricela, your eyes are brown, correct?
Mm-hmm.
I'm going to guess that your husband's eyes are also brown. Is that true?
Yes.
And then probably all your children have brown eyes. Is that true?
Yes.
Yes. Okay, now, so that was heredity. You passed on some physical traits from yourself to your children. Does that make sense?
Yes.
Okay, so same thing, but sometimes heredity gets a little confusing. So I have blue eyes, but my husband has brown eyes. So what would happen if we had a child? Well, all of our children are, we had our children before we got married, so we did it out of order. But if we went and had a child, Lord, I don't need any more, what would their eyes be like? That's the idea of heredity. Does that make sense?
Yes.
Okay, now let's read through this question here, okay? Each part of the genetic code actually consists of 2 halves known as alleles. So that's half of a gene, okay? Offspring inherit 1 allele from each parent. So you get an allele from your mother, an allele from your father. They come together to make a gene. When determining the probability of offspring inheriting certain genetic traits, scientists use capital letters to denote dominant alleles. And then they define for you what a dominant allele is, and that's super important when you go to do heredity questions, so I'll just point it out. Dominant alleles are alleles that code for traits that are always expressed. So that's like, if you have in your genes that you have brown eyes, you will always end up with brown eyes. Does that make sense?
Yes.
They use lowercase letters to denote recessive alleles. Alleles that code for traits that can be carried in genes without being expressed. So this could happen. I could pass on a blue-eyed genetic code to my daughter. In fact, I did. My daughter Ruby has a blue-eyed gene, I promise you, because I have blue eyes. However, guess what? Ruby does not have blue eyes. Ruby has brown eyes. Her dad's genes won. My gene and his gene got in a fight and he won. But she ended up with brown eyes. Okay, does that make sense?
Yes.
Okay, so it says, for example, an individual might be heterozygous brown-eyed, meaning that their genes contain both an allele for brown eyes and an allele for blue eyes. So that's my daughter. Her genetic code probably looks like this: capital B, lowercase b, brown eye, blue eye. Okay, but her eyes, how do they actually look? Well, they look brown. So a certain pea plant can produce either dominant green peas, capital G, or recessive yellow peas, lowercase g. Additionally, smooth peas are dominant, capital S, while wrinkled peas are recessive, lowercase s. How many different distinct genotypes of peas are possible? Okay, so we want to take their genes, we want to mix them up to figure out how many possible pea genotypes we have. David, did you have something to say?
Yeah, you're going to want to draw this one out, aren't you?
Yes, sir, I sure am. We want those distinct ones. I'm going to go ahead and draw them out. So let's deal with our color first. Okay, everybody's going to get 2 alleles. They get one from their mother and one from their father. Okay, so the possibility is either that they get a capital G from mom, and also a capital G from dad. And it's a mommy plant and it's a daddy plant, but you guys get what I mean. So it's possible that both the alleles are G for green. What other possibilities are there?
Big G, little g.
Mm-hmm.
And then you're going to do little g, big G, right?
Am I going to do little g, big G? Is that distinct from this one? I'm going to say no, it's not distinct. Little g, big G is not distinct from that one. It'd be the same basic genetic code. You would still have one, green and one yellow. And so I'm going to say the only other option then would be to have 2 little g's. Are you cool with that?
Yeah.
And again, it's that wording distinct. That's the same reason on that other problem with the dice, when it said distinct, I didn't want that 1, 6 confused with that 6, 1. I didn't want to count them separately. They basically give you the same results. So now, those are my 3 possibilities of that. But then when I go to combine that with my smooth or wrinkled, my big G, we're going to have 3 possibilities again. Either they're both smooth, they're both wrinkled, or we have one smooth, one wrinkled gene. Okay, awesome. So both smooth, both wrinkled, or one smooth, one wrinkled. And again, both smooth. I'm running out of room. Okay, but you guys get the idea. I end up with how many possibilities?
9.
9. And I guess you could have gotten 3 times 3 if you'd have realized that there were 3 combinations, but it took me drawing it out to see that. Easy. So it was shrouded in a lot of language. If there's any of this language that you don't know, guys, I'm just going to do this. They very, very, very commonly use this concept on the science test. In fact, I would not be the least bit surprised if you had 2 heredity problems on your GED, okay? So here's some language you need to know. I'm just going to highlight the words that if you don't know, you should know them, okay? So whoops, let me clear this. You need to make sure that you know the word allele, what it means to inherit. You need to know what offspring are. You need to know the word dominant and recessive. Another word in here that comes up in your science is heterozygous. So there's very few words that I say you actually have to have memorized for the GED. This is an exception to that rule. This is so commonly used and so frequently asked, I would say learn it. So here we go. In a certain state, license plates are created using any 3 of 24 letters. The state does not use O's or I's on plates, followed by any 3-digit number. Repeated letters and numbers are allowed. How many different license plate combinations are possible?
3 times 24 times 1.
So I agree with you that I can use the multiplying method. You're right. I can use the multiplying method. I don't need to draw out anything here. I'd be in hell if I tried to. It would take me a really long time. But I can use the multiplying method. Why? Because having an AB on your license plate is different from having a BA on your license plate. That's a different license plate. If I call an ABC to the cops, they're not looking for a CAB.
Yeah.
Okay, so those are just each one of those choices makes a difference. I could just go ahead and write my choices in order. So on this license plate, I'm going to end up making 6 choices, David. So I should have heard 6 numbers multiplying from you. First, I'm going to choose boom, 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 my letters. Then if I have a 3-digit number, guess what? I'll choose the first digit, second digit, third digit. So I'm going to end up making 6 choices. Now, you're supposed to multiply by the number of choices you have each time. So let's look at the first letter. How many choices do I have for the first letter? There are 3 letters I'm going to choose, but I have many more than 3 letters to choose from. How many letters do I have to choose from?
24.
24. Does that, and see the distinction there? That's the number I'm choosing from. So I have 3 blanks for my letters because I'm making 3 choices, but I have 24 letters to choose from. Does that make sense?
Yes.
Yeah.
Now, how about as I choose my second letter? How many choices do I have here?
23.
Do I have 23?
24.
So, or do I have, that's exactly the right question, Maricela, because there are times when you go down in your choices and there are times that you don't. And there's actually a clue in this word problem that tells you if I have 23 or 24. Do you see the wording in this word problem that clarifies it for me? Look at that second to the last phrase. Do you see repeated letters and numbers they're allowed? So can I use all 24 letters even though I already used one?
Yes.
Yes, I'm allowed repeats. And so I will put 24. And that's because of this phrase. It's okay to repeat. If it wasn't okay to repeat, well, guess what? Then I could only put 23. Yeah, but they let you have a license plate that says AAA. Why not? So then how about for my next choice? The next thing I choose is going to be a letter. So how many choices do I have for the next one?
The same 24.
The same 24. Beautiful. So in a certain state, license plates are created using any 3 of 24 letters followed by any 3-digit number. So, okay, now I'm going to follow it with a 3-digit number. So let's take a look. And why did I put 3 blanks if it's just one number?
Because there are 3 different numbers.
It's a 3-digit number. Exactly right. So that'll allow me to count up how many 3-digit numbers there are. So let's think about how many digits there could be in the first space. How many digits do we have to work with, guys?
9.
That's what students tell me all the time. They tell me 9 all the time. Maricela, you're missing a digit.
0. So it will be
Yes,
10.
don't forget that 0 is a legit digit. Is it possible to have a license plate that says 005?
Yes.
Yes, it sure is. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possibilities. You have to count 0. It is a legit digit. Okay, then how many possibilities for the next digit?
The same 10.
Still 10. Yeah, repetition's allowed. And how about for the last digit?
10.
10. And this is a giant number. I definitely want my calculator. 24 times 24 times 24 times 10 times 10 times 10. And of course, this is why we do license plate this way, because there's a lot of cars. So we need a lot of different possible license plate combinations so we don't end up repeating numbers. Okay, so now in order to read this is the answer I got out of my calculator. I'm going to start from the back and put in commas. 1, 2, 3, comma. 1, 2, 3, comma. And you and I were practicing reading these numbers out loud the other day, Maricela, but this says 13,824,000. Now, what if you're in a state like California that you need more than 13 million license plates? You know what they do? They have 7. They don't just have 6, do they? They have 7, and it's all mixed up letters and numbers. And so the more options, the huger this number gets. Okay, so whew, I'm done, guys. Is this record time? This is record time, you lucky snots.
Yeah, and I love this class. I really like this class.
Awesome. Well, I'm going to have to go use the spare time that I have to go make up a homework for you on this, because most homework that exists out on the internet for this is more complex than what appears on the GED and encourages you to memorize a formula. And I say we did all of these without formulas. We just used some common sense. And I thought it was pretty simple. So I'm just going to create some problems that are of this style. I'll just put up one at practice. Then we will see you next class. Next class, we're going to put this together with the concept of probability, which is like, what is the likelihood that this happens? Or what is the percent of the time that this probably happens? Those kind of problems, all right? So join us next week.